In this video, we're going to discuss how we can go about removing a discontinuity from a piecewise function. Specifically, how may we define a piecewise function to be continuous at a boundary to the partition of its domain? Well, that sounds kind of complicated, but essentially what we're going to do is remove these removable discontinuities. So a very typical type of question you're going to see in an AP calculus class is something where it's asking which of the following statements about a function is true. So we're talking about continuity today, so that's what this particular question is focusing on. So we have the limit as x approaches 4 of f of x exists, and f of x is continuous on negative infinity to infinity. And then some variation of one of these existing and the others not, or both don't exist. Now, just knowing our definition of continuity, one of these answer choices could automatically be eliminated because they are not possible. Even though we have no idea what the function is, we already know one of these can be eliminated. So take a moment and ask yourself, which one is not possible? Okay, so hopefully after reading them carefully, thinking about our definition of continuity, you can see that answer choice C is not our friend. Because if the limit does not exist, then there's no way that the function could also be continuous on that interval. So we're going to go ahead and just eliminate C outright before we even look at the function. So let's reveal what we're working with here. Anticipation. I feel like I'm playing the lottery. Oh, okay. All right. We're getting some. Oh, are you kidding me? Really? I must have spilled my coffee on this earlier. I do apologize. So what are we going to do now? How are we going to answer this question without every piece of information available? Well, I'm going to kind of do something crazy. I can't get rid of the coffee stain. That seems pretty permanent. But I am going to tell you that the answer to this question is A. The answer to this question is that the limit as x approaches 4 of f of x does exist and the function's continuous. So we're going to kind of turn this entire problem on its head. I'm giving you the answer, and now we're going to work backwards. So let's look at this new question I'm posing to you. So now it is stated that it's known that the limit as x approaches 4 of f of x exists, and that f of x is continuous on the interval negative infinity to infinity. Find the value of k, where k represents this secret unknown value that my coffee stain unfortunately covered up for us. Okay, so to begin this process, we're going to start with that definition of continuity, which in this case would state that the limit as x approaches 4 from the left of the function must equal the limit as x approaches 4 from the right of the function must equal the value of the function at x equals 4. And we know this to be true. This is what was given to us in the actual problem itself. So now we're going to kind of work backwards to set up some sort of system of equations that will allow us to solve for this unknown constant. So let's play with this part first. Let's try the limits. We'll come back to actually evaluating f of 4 in a moment. Okay, so for approaching 4 from the left, we're going to use values that are below 4. So we'll be using this particular function here. So we'll rewrite that as x squared minus k. And so we can do direct substitution here because this is a polynomial. And so we'll just go ahead and substitute in a 4. And we get 16 minus k. Then we're going to do the same thing for the right-hand limit. As we approach 4 from the right, we'll be using our second piece of the piecewise. So negative 3x plus 18. And that will simplify to negative 12 plus 18, which is 6. Okay, so since we know that the limit as x approaches 4 of f of x must exist, then we also basically know that these two particular left and right-hand limits must equal each other. So that allows us to set up a simple equation which we can use to solve for k. And you should see that k is going to equal 10. So this means that where that unknown constant was, where my unfortunately yet precisely placed coffee stain fell, it must be covering up a 10. And so what we have done here is we have created this piecewise so that this definition of continuity will be forced to hold true. And we're working backwards to do this. So what I want you guys to see graphically is that when we're removing these discontinuities, it typically is giving us one possible way to do this with our piecewise function. So watch what happens whenever that constant is any other value. We're going to have some sort of jump discontinuity. The only way it's going to be continuous is if we are able to get it to -10 exactly as our constant. Okay? So that's essentially what we're doing algebraically whenever we're doing these removable discontinuity problems. So what I want you to take away from this lesson is that the definition of continuity helps us ensure piecewise functions are continuous at their boundary points, where those domain splits are occurring. Now what we're going to do in class is use a calculator to do one, a little bit more complicated, and we'll see how you would use this with technology.